Can you see my screen? Oh, can you hear my sound?
Yes.
Yeah, okay.
It's okay. Please start.
Okay. Yeah, thank you for Professor Shavkat's hypothesis introduction. Also, thanks for Ewan and Jobert's invitation. It's my pleasure to give a talk here. The content of my talk is about conformal algebras. First, I introduce some background of the conformal algebras. The notion of the conformal algebra was introduced by Kass as an axiomatic description of the operator product expansion of chiral fields in two-dimensional conformal field theory. It turned out to be a valuable tool in studying vertex algebras, Poisson vertex algebras, and Hamiltonian formalism. There are two types of Poisson algebras related to the conformal algebra. One is Poisson vertex algebra. The other is Poisson conformal algebra. First, I introduced some facts about Poisson vertex algebra. This definition was given by Ben-Zevi and Franco. A Poisson vertex algebra is a Lie conformal algebra plus a commutative or associative differential algebra satisfy a Leibniz rule. There are three main constructions. One is given by filtered vertex algebra. It's constructed from the Lie conformal algebra, universal inverlooping vertex algebra. The second is given by symmetric algebras of the conformal algebra. The third is can be given from the formal vertex algebras, which are very similar to the classical Poisson algebras. A slogan was promoted by Kass is that Poisson vertex algebras in integrable system terms of PDE are similar to Poisson algebras in integrable system terms of ODE. So, Poisson vertex algebras is an important study object, but there is also another Poisson type algebras related to the conformal algebras, which is Poisson conformal algebra. Now we recall some background of Poisson conformal algebra. It's a very new object, but it's really the conformal analog of Poisson algebras. HB are Hopf algebra generated by primitive element partial. The class master H of H module forms the pseudo tensor category. Then the conformal algebra can be seen as a morphism operand from the operator Lie to M star H, similar for associative case. In particular, for morphism from the operator Poisson to M star H, Karlsnikov introduced the notion of a Poisson conformal algebra, which consists of the conformal algebra and a commutative associative conformal algebra satisfying the conformal Leibniz rule, which is very similar to the Poisson vertex algebra. It is also the conformal algebra plus a commutative associative. This is a conformal algebra. That is a commutative associative differential algebra. These are different. They are the meaning of two notions are very different. But there are also some constructions, as in the case of Poisson algebra or the Poisson vertex algebra. A series of examples of Poisson conformal algebras are given by associated graded conformal algebras of associative conformal envelopes of the conformal algebras. But this construction is different from the classic one. The conformal algebra can't be embedded into the associative conformal envelopes. It's just the injection, but not the algebraic embedding. Close relationships between Poisson conformal algebras and the implementations of the conformal algebras. Poisson conformal algebras play an important role in the study of other type problems for the conformal algebra. See this paper for more details. The following is my framework or my report for this report. First, I will give notions of Poisson conformal algebra and some constructions. Then give the deformation quantization where associative conformal algebra. Third, I will give the cohomology and deformation of NPCA. First, we recall some notions of conformal algebra. Our conformal algebra is a C-partial module. In those with a complex bilinear map from A cross A to A lambda. This A bracket lambda meaning the polynomial of lambda with the coefficients in A. We often denoted by A lambda B, satisfies the following two conditions, which is also called semi-linear condition. Furthermore, an associative conformal algebra is a conformal algebra and satisfies the following associative rule. Similarly, an associative conformal algebra is called commutative if it satisfies this condition, commutative condition. Define the nth product on an associative conformal algebra for any integer n. Define this summation for a circle lambda b. This A bracket NB is a map from A cross A to A. Then the associative conformal algebra can be facilitated in terms of nth products as follows. Furthermore, the commutative condition can be written by this formula. This condition is just the semi-linear condition. This is the associative rule. This is the commutative condition. Similarly, the conformal algebra is also a C-partial module in those with the complex bilinear map from A cross A to A lambda, which is denoted by A bracket A lambda B, such that A is a conformal algebra and satisfies the following two conditions. This is called the anti-symmetric condition. This is the Jacobi condition, identity. Also, we can define the nth product on A by this formula. Then the conformal algebra can be given as follows. Furthermore, we can give the notion of Poisson conformal algebra. In those ways are two lambda operations. One is circle lambda b, one is lambda bracket, such that this is a commutative associative conformal algebra. This is the conformal algebra and satisfying the following limit rule conditions. If the associative lambda multiplication in the Poisson conformal algebra is non-commutative, We call it a non-commutative Poisson conformal algebra, also called NPCA. Furthermore, the conformal limit rule of Poisson conformal algebra can be calculated in terms of nth products as follows. The first example is given by the direct sum. It's easier. The second example can be constructed by ordinary Poisson algebra. Then P is the partial tensor A equipped with the operation as follows. Is a Poisson conformal algebra. The general formula for this lambda multiplication can be extended by the semi-linear condition. This example for classical case is well known. But for conformal case is also true. Let A be an associative conformal algebra. Then A is an NPCA, where lambda bracket is given by this case. The following construction is important in the conformal algebra. It's called a quadratically conform algebra, which is the conformal algebra A is of this form, with the free partial module, and the lambda bracket is of the following form. Similar to this definition, we give the quadratic Poisson conformal algebra. If the associative conformal algebra in this Poisson conformal algebra is a current associative conformal algebra, it's meaning the lambda operation is given this form. And the conformal algebra in P is a quadratically conform algebra. Then P is called a quadratic Poisson conformal algebra. This definition was recovered by Zhang Zhang, so I omit this definition. It's well known that the quadratically conform algebra can be equivalent to the Gelfand-Dorfman bi-algebra. So we recall this notion, which is a triple, such that A bracket is a Lie algebra, A star is a Novikov algebra, and satisfy the following condition. This proposition was given by Gelfand, Dorfman, and Xiaoping Xu, which gave an equivalent description of the conformal algebra. The conformal algebra is quadratic if and only if V is a GD algebra, where the correspondence is given as follows. Similar to the above proposition, we also give an equivalent description of Poisson conformal algebra. A Poisson conformal algebra P is quadratic if and only if this is a GD algebra. We equipped with this multiplication and bracket is a Poisson algebra and satisfy the following equations 1 and 2. This condition is just the differential Poisson algebra was given by Zhang and its co-authors. So our differential Poisson algebra can give rise to this notion PGD algebra. Our PGD algebra is a quadruple such that this is our GD algebra. This is our Poisson algebra satisfying 1 and 2. The following example of proposition was given by Kolesnikov for Poisson conformal algebra. I note this example can also give a PGD algebra. Let A be a Poisson algebra with a derivation D. The operation this makes the A being a PGD algebra. Furthermore, this is a Poisson conform algebra. The lambda operation is given like this. The lambda bracket is given like this. As a corollary, let A be a commutative or associative algebra with a derivation D. Then A is a PGD algebra. The bracket is the trivial. Furthermore, our Poisson conform algebra, the lambda operation and bracket are given as follows. So there are many examples of Poisson conform algebras. We know that from our Lie conform algebra, we can get our Lie algebra. Similarly, from our Poisson conform algebra, we can also construct Poisson algebra, which is called coefficient Poisson algebra. Let A be a vector space. Denote this by the quotient of the subspace vector space with the basis an. A is in A, n is integer. By the subspace spanned over C by elements as follows. Then let P be a Poisson conform algebra. Then the coefficient P with the following multiplication and bracket is a Poisson algebra, which is called coefficient Poisson algebra. These two constructions for conformal associative algebra and the conformal algebra are given by Katz. For this Poisson conformal algebra, the corresponding coefficient Poisson algebra is given as follows. Second, for every Poisson conform algebra, we can obtain a new Poisson conform algebra, which is a quadratic Poisson conform algebra. Like this, define D on the coefficient space from here to here by this. Then D is a derivation on the Poisson algebra. Furthermore, we can get a new Poisson conformal algebra like this. Second, we will study the deformation quantization while associative conformal algebras. First, we record the module over an associative conformal algebra, which are a pair of complex bilinear maps, A circle lambda V and V circle lambda A, satisfying the following conditions. Now we recall the cohomology theory of conformal algebras. Let A and V be the partial module. For n is more than or equal to 1, and n lambda bracket on A with the coefficients in V is a complex linear map denoted by this form, satisfying the following conditions. If we put partial in the first n-1 place, then we put here minus lambda I. If we put a partial in this place, then the coefficient here is like this. Furthermore, let A be an associative conformal algebra and V a module. We let CH0 AV is be V over partial V. And for n is greater than or equal to 1, we denote by CHN the space of all n lambda brackets on A with the coefficient in V. For elements in CH0, Then the corresponding DH is defined by this formula. For gamma in CHNAV with n is more than or equal to 1, the corresponding conformal hot-killed co-boundary operator is defined by this formula. It's very similar to the classic one, but without some lambda I. The denoted by the H dot, the cohomology of the associative conformal algebra A. Now, we recall some facts. Let A be an associative conformal algebra. It's well known that A double bracket H bar is the formal power series of H bar with the coefficients in A. It's the completion of the CH bar module with respect to the H bar artic topology. Formally, we can extend the associative conformal algebra lambda operation to this bilinear lambda operation on this space as the following. Because this lambda operation in general involves infinite numbers of powers of lambda. So this space doesn't carry the structure of the associative conformal algebra because the associative conformal algebra the lambda operation in the space of polynomial space, not in this formal power series of lambda. To overcome this problem, we introduce this definition. An H-artic associative conformal algebra is a CH bar module, this A double bracket H bar, where A is a vector space equipped with the H bar artic topology. This module structure and continuous bilinear lambda operation on this space, such that for any n is an integer, this space with the following lambda operation is an associative conformal algebra. This is no problem because this subspace is in the polynomial space, in the polynomial of lambda. Now, the remark is given that this be an H-artic associative conformal algebra for every pair of negative integers I and g with I is less than or equal to g. The natural map pi ig from this onto this is an associative conformal algebra homomorphism over this space. The associative conformal algebra this together with these morphisms form an inverse system. Then the H-artic associative conformal algebra can be seen as an inverse limit of the associative conformal algebra. This. Now we give the main definition in this section. Let A be a commutative associative conformal algebra. A conformal formal deformation of A is a continuous bilinear lambda operation. This such that this space carry the structure of an H-artic associative conformal algebra, where this operation extends natural to a continuous CH bar map on this space, such that the following formula holds, where mu n is a map from A cross A to A lambda, with mu 0 being the commutative associative lambda operation on A. It's very similar to the classical one, except this structure. Now let this be a conformal formal deformation of A. Define the bracket as following. Then A equipped this lambda operation and this lambda bracket is a Poisson conformal algebra, which is called the semi-classical limit of this. The HRDic associative conform algebra is called a deformation quantization of A. In the following, we study the deformation of associative conform algebra and the deformation of classical algebra through the coefficient algebra. Let this be a conformal deformation of A. The coefficient commutative associative algebra on this space is given by this formula. Furthermore, the coefficient associative algebra on this space is given by this formula. It's not hard to see that this is an associative formal deformation of the coefficient associative algebra. Furthermore, we define the bracket on this space by this formula. Then, this is also a Poisson algebra, which is a semi-classical limit of this algebra. So there's some relation between the Poisson conform algebra and Poisson algebra. Similar to the classical one, we can also study the conformal N deformation. Let A be a commutative associative conformal algebra. A conformal N deformation of A is a sequence of bilinear map mu I from A cross A to A lambda. I is more greater than or equal to 0, is less than or equal to N, with mu 0 being the commutative associative conform algebra lambda operation, such that this lambda operation determined by this formula is an associative conform algebra lambda operation. It's very similar to the classical one. Our conformal one deformation of our commutative associative conformal algebra A is called our conformal infinitesimal deformation, and we denote it by A mu1. Two conformal infinitesimal deformation AH bar and AH bar prime of our commutative associative conformal algebra are said to be equivalent if there exists a family of conformal algebra homomorphism ID plus H bar phi from this to this. This needs to module H bar square. Now we can obtain the following theorem. There is a one-to-one correspondence between the space of equivalence class of conformal infinitesimal deformation of A and the second cohomology group H2AA. It's coincide the classic case. Let mu1 C dot mu n be a conformal N deformation of our commutative associative conform algebra. Our conformal N plus 1 deformation of our commutative associative conformal algebra A given by this is called an extension of the conformal N deformation given by this. For any conformal N deformation of our commutative associative conformal algebra A, the map theta n in this space is a three coating determined by this formula is a three co-cycle. Moreover, the conformal n deformation mu1 c dots mu(n) extends into some conformal n+1 deformation if and only if this class in H3AA is 0. At last, we give the cohomology and deformation of NPCA. First, we recall the module over the conformal algebra. Our module V over the conformal algebra A is a C partial module. In those with a C bilinear map, we denoted by A lambda V, satisfy the following conditions. It's very similar to the condition of the conformal algebra. Now, we also recall the cohomology theory of the conformal algebra. The cohomology complex for the conformal algebra A with a module V in the language of lambda brackets is given as follows. We also let CE0 AV by V over partial V. And for K is more than or equal to 1, we denote by this symbol, which is the space of K lambda brackets on A, with the coefficients in V satisfying the extra condition. This is just the anti-symmetric condition. It's a little complicated. This formula is given by Katz and co-authors. The corresponding conformal Taylor-Ellenberg co-boundary operator is defined by this. It's similar to the classical one, but it's somewhat different from the formula given the classical, because we need to deal with the lambda I and the special lambda k plus 1 diagram in this case. We denote by HCE dot the cohomology of the conformal algebra A with the coefficients in A, this symbol. Now we give the module of NPCA. Let P be our NPCA. Our module V over P is our C partial module. In those with maps A circle lambda V, V circle lambda A, and A lambda V, such that V is both the module over the associative conformal algebra P circle lambda and the module over the conformal algebra P bracket lambda bracket, satisfying the following three conditions. Now we give the cohomology of NPCA. First, we give the cotines. Let P be our NPCA and V are module over P. We denote the M plus N lambda bracket on P with the coefficients in V by this form, like this. In particular, M plus 0 lambda bracket, meaning lambda N is 0. With it's called M0 coating if gamma satisfies the following anti-symmetric condition, which is just the conformal algebra case. If N is not 0, N is not 0, M plus N lambda bracket gamma on P with the coefficients in V is called MN coating if gamma satisfies the following anti-symmetric condition. It's different from different at last element. This is the sigma m. Here is the sigma m. If paired this element lambda m should be replaced by lambda m diag. This is more complicated, but this no that case. It's more easier to deal with. Denoted by the CMNPV, the space of MN cochains, denoted by CFGVK PV, is the sum of this element with the condition m plus n is equal to k and m is not equal to 1, which is just the space of k cochains. The cohomology of the MPCA is illustrated by the following diagram of bicomplex. See the horizontal direction. This is controlled by the Lie path, by the Shirley Ellenberger coboundary operator. Then there are some a little different. See the vertical direction, which was controlled by the Hochschild coboundary operator. The details see following there for more details. The Conformal Flight Gersten-Haber-Vernoff coboundary operator DFGV from this space to this space is defined by the following formula. It's just the consequence of the bicomplex theory. In this formula, the for n is equal to 0, then DCEMN from CMN to CM plus 1n is given by the conformal Shirley Ellenberger coboundary operator. For n is greater than or equal to 1, it's defined by this formula. This is obtained by the module of by special module of the conformal algebra. So there's a little complicated. For the above formula is correspond to the horizontal direction. The following is the vertical direction. For n is greater than or equal to 2, is defined by the conformal Hochschild coboundary operator, given as follows. It's very similar to the classical case, except some lambda and mu. In particular, for this coboundary operator, it should be defined specially. DHM1 minus 1 here operator, coboundary operator should be defined specially. We first need to expand C10 into the space of C11 space, or this C20 to C11 space here. So this is the just that means this we can expand this space into this space, and the conformal Hochschild coboundary operator DH from this to this. So then we can obtain the DHM minus 1. With the above notations, we have DFG circle DFGV is 0. That is, we obtain the cochain complex. Let P are NPC, V are module over P. The cohomology of the cochain complex is called the noncommutative Poisson conformal complex of P with the coefficient in V. The corresponding case cohomology group denoted by this is called the noncommutative Poisson conformal cohomology. Now we use the above cohomology to study the deformation of NPCA. Let P are NPCA are conformal infinitesimal deformation of P is a pair of bilinear maps y pi omega from P tensor P to P lambda such that this bilinear lambda operation H circle H bar lambda and lambda bracket this on this space determined by the following formula. This is the lambda operation. This is the lambda bracket. Define our NPC structure on this space. It's similar to the classical case. Then, if y pi omega generates a conformal infinitesimal deformation of the NPCP, then omega plus y pi is a 2 cocycle for the NPCP. Conversely, any conformal infinitesimal deformation is obtained by a 2 cocycle in this way. We can also give the definition of equivalent of 2 deformation. 2 conformal infinitesimal deformation PH bar and PH bar prime of the NPCP, which are generated by y pi omega and y pi prime and omega prime, are said to be equivalent if there exists a family of NPCA homomorphisms ID plus H bar 5 from this to this module H bar 2. Then we can obtain the following theorem. There is a one-to-one correspondence between the space of equivalence class of conformal infinitesimal deformations of the NPCAP and the second cohomology group. Okay, that's all my report. Thank you.
Thank you very much, Dr. Liu. So any questions or comments? So if there is no questions, let us thank Professor Liu, our speaker, for a very interesting talk. Thank you very much.
Thank you. Thank you.
Thank you.